Good day everyone and welcome. Today, we delve into the fascinating world of scientific language models with our presentation titled Galactica, a large language model for science. This groundbreaking research explores how language models, like Galactica, can revolutionize the way we access and explore scientific knowledge, breaking free from the limitations of traditional methods. Stay tuned as we unravel the potential of these models to absorb vast amounts of technical knowledge, predict citations, and bridge the gap between scientific modalities and natural language. Let's embark on this scientific journey together. The traditional method of accessing scientific knowledge has its limitations. It relies heavily on human effort to reason, combine, and organize information, creating a bottleneck in knowledge throughput. Language models, however, have shown promise in disrupting this paradigm. They've been used successfully in citation prediction and knowledge-intensive question-answering tasks, demonstrating their ability to absorb and utilize technical knowledge. Furthermore, initial investigations have shown the potential of language models to act as a bridge between scientific modalities and natural language. Despite these advancements, there are still challenges to overcome. Existing methods require significant human effort, and there's a lack of a mechanism for continual learning and incorporating new scientific knowledge. Additionally, verifying the accuracy and factual correctness of language model generations remains a challenge. These are the problems we aim to address in our research. Our research proposes a novel approach to accessing and exploring scientific knowledge, using language models as a tool. We've developed a method that involves a working memory token approach, and we've trained our model on a variety of datasets, including PubChem compound, UniProt, and RefSeq genome. The technical results of our work are quite promising. Our language model has demonstrated strong capabilities in absorbing technical knowledge. It has outperformed tuned, sparse, and dense retrieval pipelines for citation prediction, a significant achievement. Furthermore, our model has been able to compose a curated knowledge base, performing exceptionally well in knowledge-intensive question-answering tasks. This indicates a promising future for language models in the realm of scientific exploration and discovery. For many decades, our access to scientific knowledge has been largely dependent on a store and retrieve paradigm. This method, while effective, has its limitations. The process of reasoning, combining, and organizing information still heavily relies on human effort. This reliance creates a significant bottleneck in our ability to process and utilize knowledge. As we delve deeper into the era of information, it's crucial that we explore new ways to streamline this process and overcome these challenges. The image here illustrates the concept of multimodal data, a key element in our approach to this problem. Language models hold immense potential to revolutionize the way we access and explore scientific knowledge. They can disrupt the traditional paradigm, absorbing large bodies of technical and scientific information, and performing exceptionally well in knowledge-intensive tasks. However, the current approaches, such as search engines and databases, have limitations. They heavily rely on human effort and are often inefficient in reasoning, combining, and organizing information. Our proposed method addresses these issues by harnessing the power of language models. We introduce a working memory token approach that has shown strong performance on various benchmarks. Furthermore, we train our models on diverse datasets, including PubChem compound, UniProt, and RefSeq genome, to ensure a broad and comprehensive understanding of scientific knowledge. This approach paves the way for a more efficient and effective exploration of scientific literature. Our research has shown that language models have a surprising ability to absorb and utilize technical knowledge. This is evident in their performance in predicting citations and their effectiveness in knowledge-intensive question-answering tasks. They can even handle complex tasks, such as interpreting LaTeX equations and chemical reactions. We've also begun to explore the potential of large language models, or LLMs, to act as a bridge between scientific modalities and natural language. For instance, our model Galactica has shown promise in learning tasks like IUPAC naming through self-supervision. This opens up exciting possibilities for tasks such as automatic protein annotation and drug discovery. In essence, we're seeing that language models have the potential to revolutionize how we access and interact with scientific knowledge. Our research proposes a novel approach to accessing and exploring scientific knowledge using language models. We've developed a working memory token approach that has shown strong performance on various benchmarks. Our model is trained on a diverse range of datasets, including PubChem compound, UniProt, and RefSeq genome, to ensure a broad knowledge base. Diving deeper into our methodology, we've trained our language models to absorb technical knowledge. This includes complex elements like LaTeX equations and chemical reactions. Our aim is to outperform existing retrieval pipelines for tasks like citation prediction. Furthermore, our models are trained to compose a curated knowledge base, enabling them to perform well on knowledge-intensive question-answering tasks. This approach opens up new possibilities for exploring the vast body of scientific literature. Our research presents a unique approach that disrupts the traditional store and retrieve paradigm of accessing scientific knowledge. We leverage the context-associative power of language models, offering significant advantages over search engines. Our models are designed to absorb large bodies of scientific knowledge and excel in knowledge-intensive tasks. In terms of experiment design, we evaluate our model's performance based on its ability to absorb technical knowledge, predict citations, and perform well in knowledge-intensive question-answering tasks. We also conduct initial investigations to explore the potential of large language models, or LLMs, to bridge scientific modalities and natural language. This approach opens up new possibilities for how we interact with and utilize scientific knowledge. Our research introduces several improvements and innovations in the field of language models. We've developed a working memory token approach that has shown strong performance on various benchmarks. This approach allows the model to compose knowledge in a step-by-step reasoning manner, which has proven to be highly effective. We've also explored the potential of large language models, or LLMs, to act as a bridge between scientific modalities and natural language. This has opened up exciting possibilities, such as automatic protein annotation and formulating drug discovery tasks in a natural language prompt. Lastly, we've delved into the realm of continual learning. This involves the question of whether we should retrain models from scratch to incorporate new scientific knowledge, or train from older checkpoints. This is an open question, and we believe further research is needed to find the best procedure for incorporating new knowledge into the model. These innovations are paving the way for a new era of language models that are more efficient, accurate, and versatile. Our research has yielded some key results that we're excited to share. Firstly, we found that language models are adept at absorbing technical knowledge, including complex LaTeX equations and chemical reactions. This ability to process and understand intricate information sets them apart. Secondly, our model surpassed tuned, sparse, and dense retrieval pipelines in citation prediction. This demonstrates the potential of language models to revolutionize how we explore literature and scientific knowledge. Thirdly, our model was able to compose a curated knowledge base, performing impressively in knowledge-intensive question-answering tasks. This shows the potential of language models to take on tasks that are currently human specialisms. Lastly, our initial investigations revealed the potential of language learning models, or LLMs, to bridge scientific modalities and natural language. This opens up exciting possibilities for tasks such as automatic protein annotation and drug discovery. In summary, Our research suggests that language models have the potential to significantly disrupt the way we access and process scientific knowledge. Diving into the technical results, our findings suggest a promising potential for language models to revolutionize the traditional method of accessing scientific knowledge. Instead of the store and retrieve paradigm, language models offer a context-associative power that could provide significant advantages over search engines. Moreover, these models have shown an impressive ability to absorb large bodies of scientific knowledge. This capability, coupled with their performance in knowledge-intensive tasks, indicates that language models could become a valuable tool for exploring scientific literature. However, as we move forward, it's crucial to address certain challenges. We need to conduct further research to determine the best procedure for incorporating new knowledge into the model. Additionally, it's essential to verify the accuracy and factual correctness of the generations produced by these language models. In essence, our results highlight the potential of language models and the need for continued research and development in this field. Our research has shown that language models have the potential to revolutionize the way we access scientific knowledge. Instead of the traditional store and retrieve paradigm, these models can absorb and organize technical knowledge, such as LaTeX equations and chemical reactions, in a more efficient manner. In our study, we found that our language model outperformed other methods in predicting citations, demonstrating its potential as a valuable tool for exploring scientific literature. Furthermore, the model showed a strong ability to compose a curated knowledge base, performing well in knowledge-intensive question-answering tasks. We also began to explore the potential of large language models to bridge the gap between scientific modalities and natural language. This is an exciting area of research with many possibilities. As you can see in the figure, the distributional comparison of citations further illustrates the effectiveness of our approach. In conclusion, our work suggests that language models could play a significant role in the future of scientific research and knowledge discovery.